In this lecture, we talk about some astrophysics, or if you want to make it more complicated, astrology and cosmology. Basically, this is the branch of physics where you start looking at outer space, the stars, the planets, and the galaxies. We start with the idea of a standard candle. So it says on the screen that flux or intensity of radiation coming from a star is defined as the power acting per unit area on a detector. Flux or intensity of radiation coming from a star is defined as the power acting per unit area on a detector. And the luminosity of a star is found using the formula F equals to L over 4 pi d squared, where F is the flux, L is the luminosity. And you can expect that the more energetic a star is, the brighter it would appear, because more energy is being given off from it and being received per unit area on a detector, right? Now we have this concept called a standard candle. First of all, you need to understand, before you can understand the standard candle, understand parallax method. In the parallax method, we observe the star from the opposite sides of the Earth's orbit around the sun. So let's say the sun is right here in the middle, and the Earth is right here on the left on 1st July, and then right here on 1st January. So it goes from one side of the sun to the other. Remember, the sun is static. It's not really orbiting anything. It's a star, giant star, and it's the Earth technically which is rotating around the sun. So it's going to move around from one side to the other. And let's say there's also another nearby star fixed at its position. Now, fixed in terms of orbit, it's not orbiting something, but keep in mind that there is this general notion that the universe is expanding. So everything in our observable universe is moving further away, right? How fast depends upon the speed. So let's say there is this nearby star at a distance d from the sun. Let's say that if we draw a dotted line from that star towards the Earth as of 1st July and as of 1st January, the angle is alpha with respect to the vertical line or a normal line drawn through the Earth on 1st July and 1st January. See that they intersect at the star and they kind of create a triangle, whereby we can say R is the distance between the center of the Earth and the sun. D is the distance from the center of the sun to the nearby star center. And if we extend these dotted lines, they'll go behind and basically, let's say, represent some distant stars A and B. So we observe the star from opposite side of the Earth's orbit around the sun and make careful measurements of its apparent position. We then calculate the distance using some trigonometry. As you know, once you get a right angle triangle, your sines and your cosines and your tans can play a role, right? Since you already know the distance between the Earth and the sun in terms of the Earth's orbit, so that makes the rest of the job easy. Using a standard candle, the luminosity of some stars can be found from other measurements, perhaps a particular spectrum of radiation they emit or a regular variation in their brightness, which can be matched to that of known stars. We can always measure the flux from a star, so knowing F and L, we can calculate the distance D. Now, the whole idea behind this exercise is to calculate the distance D from the sun to the star. For example, at the top of the Earth's atmosphere, the intensity F of the sun's radiation is about 1.4 kilowatt per meter square. The distance from the Earth to the sun is 1.5 into 10 to the power 11 meters. Calculate the sun's luminosity. So you use the formula F equals to L over 4 pi d squared. Rearrange to make L the subject of the formula. It becomes 4 pi d squared F. 4 pi is multiplied with the given distance, 1.5 into 10 to the power 11 squared, times the given flux, 1.4 kilowatt per meter square. And your final answer is 4.0 into 10 to the power 23 kilowatt. This is the sun's luminosity. Notice the unit. Luminosity is more along the lines of power in watts, whereas flux is more along the lines of power per unit area, watt per meter square. That's kind of the difference between F and L. One is capturing the idea of power, the other is capturing the idea of power per unit area. And just before we go ahead, I want you to remember the idea of the standard candle. This can be asked in the exam very often. The luminosity of some stars can be found from other measurements based upon the particular spectrum of radiation they emit or a regular variation in their brightness, which can be matched to that of known stars, right? And we can always measure the flux from a star, so knowing F and L, we can calculate D, the distance. So a standard candle is based upon the idea whereby we can compare the luminosity of some stars to a known star's brightness, which allows us eventually to calculate the distance D based upon the values of F and L, which we already would know. And then we talk about some laws about radiation. First of all, we have got the Stefan-Boltzmann law. And the radiation from a star follows the laws of black body radiation. Stefan-Boltzmann law says that L is equal to sigma times T to the power 4 into surface area. For a sphere, L is equal to 4 pi r squared times sigma times T to the power 4. Now here, T is the Kelvin temperature of the star's surface. Sigma is called the Stefan-Boltzmann constant, and it has a value of 5.67 into 10 to the power minus 8. And as you know, constants are given to you in the exam. You can see the graph as well that emerges from the Stefan-Boltzmann law. There's energy output on the y-axis, and there is wavelength on the x-axis. Now, generally, you know that a shorter wavelength represents more energy, right? So you can see that when you're looking at a shorter wavelength, you're looking at a temperature on the surface which peaks to a high value like 6,000 kelvins. And as the wavelength is increasing, the temperature is decreasing. I would also recommend that you sketch this graph in your notes, so that in case they ever ask you to label such a graph or to sketch some missing portions of the graph, you should be able to do that. As the lambda is increasing, you can see that the graph is shifting down and to the right. The peak is reducing, the graph is also kind of moving to the right. And also, the initial graph is kind of asymmetric. As you go down to a higher wavelength, the graph is kind of becoming more evenly distributed, more symmetrically distributed. You can also add to your notes as I speak the definition of a black body. So a black body can be defined as an ideal object that absorbs all electromagnetic radiation that it comes into contact with. Right, so we can often model stars as a black body, meaning they absorb all electromagnetic radiation that they come into contact with, and then over time they will emit this in the form of thermal radiation over a range of frequencies, giving different colors to different stars, right? Because colors are decoded by the observer. So when different frequencies of light are being received in our eyes, let's say, we see different colors being given out by different stars, and they would correlate with the level of energy, electromagnetic energy they absorbed in the first place, which dictates their surface temperature as they emit varying degrees of thermal energy in various frequencies, which kind of gives different colors to different stars. But the whole idea is that as the wavelength is going to increase, the energy output will decrease. Another angle that I also want you to know when you think of a star as a black body is that it is a perfect absorber and a perfect emitter of energy. And before we look at the next law, let's also quote down a simple definition of the standard candle so that whenever you see this in the exam and you're asked to define it, you can do that precisely. So a standard candle is an object in astronomy that has a known absolute magnitude or known luminosity, you might say. A standard candle in astronomy is an object with a known luminosity. But we have also gone in more detail over here on the slide. But in its simplest form, you can talk about the standard candle being an object with a known luminosity, or a source with a known luminosity. After the Stephan-Boltzmann law, we look at the next one that we need to know. For Stephan-Boltzmann law, I would recommend that you pay attention to the relationship between L and T, because sigma is the Boltzmann constant and pi is also a constant, and for a specific object, you can pretty much expect the area of you can say the formula for the area to be kind of a specific thing too, like normally we'll use the surface area of a sphere, 4 pi r squared. So the main relationship here is between L and T. So we can say that L is directly related with T, or directly, I won't say directly proportional, I would say L is positively correlated, or L is proportional to T to the power 4. That's much better. So luminosity L is proportional to T to the power of 4, which means that each time temperature goes up, its impact on luminosity is 10 to the power 4 times. And then we talk about Wien's law. It says that the maximum wavelength times the temperature equals some constant 2.898 times 10 to the power minus 3. Where lambda max is the wavelength at which the energy output peaks. So lambda max is not just some highest wavelength, it's rather the wavelength at which the energy will peak. Using the equations above, calculate the wavelength at which the sun emits maximum energy, given that the radius is 6.96 into 10 to the power 8. So we can say lambda max times T equals the constant given to us, 2.898 into 10 to the power minus 3. And we can divide this with 5,800, and we get lambda max as 5 into 10 to the power minus 7 meters. So we're dividing with the temperature here. So let's say we've been given the temperature as well. The example doesn't quote that, but let's say we know that, because we can't have two unknowns in one equation. To work out lambda max, we divide the constant with the given temperature, 5,800 Kelvin, and we get lambda max as 5 into 10 to the power minus 7 meters. But the idea is that you'll have to be given the temperature, or from something like the Stephan-Boltzmann law, you'll of course work it out. After that, we talk about a very crucial concept called the redshift. You would probably know that in astronomy, it is a generally accepted theory that the universe is expanding. The evidence for the expansion of the universe comes from this concept of the redshift. Students who are familiar with the Doppler effect will find the redshift kind of similar. Light from distant galaxies contains lines whose wavelengths are stretched compared with those of nearby galaxies. The stretch or redshift, which is represented by the letter Z, is related to a galaxy speed v from away from us, provided v is much less than the speed of light. Now, the formula for the redshift z is that it is equal to the difference in the wavelength between the original wavelength and the observed one divided by the original, and that is equal to the velocity of the galaxy divided by the speed of light. Naturally speaking, when a galaxy is giving off light, the light is reaching us at a particular speed. But by the time the light has reached us, it has traveled a long distance. And in the meanwhile, the galaxy would have moved away from its current position. So we can say that the galaxy that we observe is not actually on the position where we are observing it. It must have moved far away, because there is a delay between the light traveling away from the galaxy, covering lots and lots of light years of distance before it reaches us, right? Even a lot of the stars we see up in the sky may not actually be there anymore, because we are only looking at the light they have given off. What if they had died long time ago? Because they're too far away from us, the light takes a long time before it reaches us. We think that the star is there. It may have died, gone past its stage where it was a bright glowing star. But we are receiving the light late because it is coming from a too far away point of view, right? Measurements of redshift and the distance of the galaxy from us show that the greater the distance, the greater the redshift. Galaxies are moving apart and the universe is expanding. So a redshift is pure evidence of an expanding universe. Then we talk about Hubble's law, which says that the proportional relationship between recession speed v and the distance d is the Hubble's law. The gradient of the graph, when you plot the recession speed in kilometers per second on the y-axis and the distance measured in parsecs, where 1 parsec is 3.09 into 10 to the power 16 meter on the x-axis, then the gradient of such a graph is known as the Hubble's constant h0. Astronomical distances are commonly expressed in parsecs or megaparsecs, and recession speed is typically quoted in kilometer per second. So the recession speed or the recession velocity is equal to the Hubble's constant, which is the gradient of this graph, times the distance d. You can also add to your notes as I speak the definition of recession speed. The recession speed or recession velocity is the rate at which a galaxy or any astronomical object becomes more distant from an observer as a result of the expansion of the universe. Right, so we're talking about the rate at which some galaxy or any astronomical object becomes more distant, further away from us because of the expansion of the universe. So in simple terms, it is measuring how fast is something moving away from us due to the expansion of the universe. For example, it says light from a distant galaxy has an emission line with wavelength 449 nanometers. The line has wavelength 410 nanometers when measured in the lab. Using the Hubble's constant as 71 kilometers per second mega per sec, calculate A, the galaxy's redshift and its recession speed and its distance. So you can find the difference in wavelength 445 minus 410 as 35 nanometers. Then you can divide this with, by the way, this is 35 nanometers, not millimeters, 35 nanometers with 410, where 410 is the original wavelength. Why is 410 the original? Because this is the one we initially measured. But now the emission line spectrum is giving us 445 nanometer. So we get 0.0854 as the redshift. To find the recession speed, use V equals to speed of light into z, because we know that z, the redshift, is also equal to the speed of the galaxy or the object over the speed of light. So z is 0.0854 multiplied to the speed of light 3 into 10 to the power 8. You get the speed of the object 2.56 into 10 to the power 7 meter per second, or as normally quoted, 2.56 into 10 to the power 4 kilometer per second. You can convert that by dividing with 1000 into kilometer per second. And the distance can be calculated by the Hubble's law. We have the velocity divided with the Hubble's constant, 71 kilometers per second mega per sec, 360 mega pc is your distance here. So these are the types of calculations that they can expect you to perform based upon these laws. You should also know that, in summary, the Big Bang theory, which is the widely acceptable theory of how our universe was formed, says that long time ago, billions of years ago, all that exists in our universe was matter condensed at one point known as the singularity. Then an explosion propelled that matter outwards, and over time the matter slowed down, formed planets and stars and so on, and it continues to expand outwards as supported by the redshift. So this Big Bang theory is the widely accepted theory of how our universe was formed. Now, we look at a specimen paper for 2022 A2 Physics. And this is how it can potentially test you on this topic. It says a star has a luminosity that is known to be 4.8 into 10 to the power 29 watts. A scientist observing this star finds that the radiant flux intensity of light received on Earth from the star is 2.6 nanowatt per meter square. So they're giving you F, they're giving you L. Name the term used to describe an astronomical object that has a known luminosity. You know that standard candle is the term we use for an object that is of a known luminosity. There you go. Determine the distance of the star from the Earth. So they're giving you the L and they're giving you the F value. You can use F equals to L over 4 pi d squared to get the distance as 3.8 into 10 to the power 18 meters. Simple. The sun has a surface temperature of 5800 Kelvin. The wavelength lambda max of light for which the maximum rate of emission occurs is 500 nanometer. The scientist observing the star in A finds the wavelength for which the maximum rate of emission occurs from the star is 430 nanometer. Show that the surface temperature of the star in A is approximately 6700 kelvins. So they've given you the sun's temperature, they've given you lambda max as 500, they've given you the emission 430 nanometers. So here is what you can do. Using Wien's displacement law, lambda max is proportional to 1 by T. So T is equal to 5800 times 500 over 430. 5800 is given to you, 430 is also there, and 500 is also there. So 5800 is multiplied with 500 and divided by 430. Because both are in nanometers, you don't need to convert anything here, and you get 6700 Kelvin. So yeah, this is another way of looking at this law, that lambda max is proportional to 1 by T. In our line of reasoning, we have said that lambda max times T equals to a constant, and that is because, of course, they are proportional, right? Use the information in A and B1 to determine the radius of the star. So what did you find in A? You found the distance D from the star and the Earth. And now you need to find out the radius. You can, of course, model that as a sphere. So L equals to 4 pi r squared sigma T to the power 4, Stefan-Boltzmann law. 4.8 into 10 to the power 29 is the luminosity. 4 pi into basically r squared, which is unknown, and temperature is 6700 kelvins to the power 4, and basically sigma is the constant given in the exam, 5.67 into 10 to the power minus 8, and that means you get r as 1.8 into 10 to the power of 10 meters. So these are the ways in which they can test you on these concepts. Of course, doing these questions 2 to 3 times gives you more confidence and command on how these laws are applied. And just for the sake of additional understanding, I'm taking you through a bonus piece of information. Not compulsory to know this, but for those who are curious. There's a way in which we can calculate the age of the universe. We can divide d with v, and it is equal to 1 over the Hubble's constant. Now there are 3 scenarios about what can happen to our universe. If we assume an open universe with least possible mass, then it will keep on expanding forever, but the expansion will slow down over time, meaning we have a small amount of mass expanding over a large space. A flat or critical universe with a lot of mass will stop expanding, but only at an infinite time in the future. Too far away in the future, but it will stop at some point. A closed universe with the highest mass will stop expanding and then start contracting. Why will it do that? Not a problem to deal with, but these are the possible scenarios. As you know, based upon the Big Bang theory, we are expecting that the universe continues to expand as depicted by the redshift, but the expansion may slow down over time, but it will continue to expand indefinitely. But this is extra information. You should focus on the laws and the content we have done up till the Big Bang theory. Do the question that we have gone through a couple of times to make sure you get a hold of how they can test you on this particular topic.